This is the first video for the energetics of ring flipping in bis-cyclopentadienyl titanium pentasulfide. This video will give an introduction to our system of study and an overview of the synthesis. The second video will cover NMR analysis and how to determine the activation energy, delta G, delta H, and delta S associated with the ring flipping process. What is ring flipping? A chair-to-chair ring flip is the conversion of one six-membered ring chair conformation into another by rotation around single bonds. If we look at our ring system here, we can see that this part of the ring is facing up a little bit and this side of the ring is facing down. So you can imagine sitting right here with your back resting here and your legs coming down here. After the ring flip, you can see that this sulfur is pointing up now and the titanium atom is pointing down, and your back would be resting here and your legs would be down here. After the ring flip, two cyclopentadienyl rings attached to the titanium atom flip from the axial to the equatorial position. So here, before the ring flip, this cyclopentadienyl ring was in the equatorial position, but now after the flip it's in the axial position. And this cyclopentadienyl ring that was in the axial position is now in the equatorial position. Now, there's a certain amount of energy needed to reach the transition state for this ring flipping process. And this is going to be our activation energy. So we'll be studying the chair-to-chair ring flip of bis-cyclopentadienyl titanium pentasulfide. And these two cyclopentadienyl rings are going to switch from the axial to the equatorial position during this ring flip process. And so our ultimate goal will be to determine the activation energy necessary for the ring flip to occur. And we're also going to determine the thermodynamic quantities delta G, delta H, and delta S associated with the transition state of this process. What hydrogen atoms will be producing an NMR signal? The only hydrogen atoms in this molecule are contained in the cyclopentadienyl rings. If we start with a cyclopentadiene molecule and we remove a proton from this molecule, we end up with an aromatic system, and the pi system has 6 electrons associated with it, and now there's just one hydrogen associated with each corner of the ring. The nature of the bond between the cyclopentadienyl rings and the titanium atom. There are 3D orbitals on the titanium atom that can interact with the pi system of the ring. Because the bond is not associated with a single carbon atom, the rings can spin freely, much like a plate on a stick. As a result, only one proton signal is seen for each pentadienyl ring, and the two rings produce slightly different NMR signals due to their axial and equatorial positions. Synthesis of the compound. This is a two-step synthesis, both of which need to be done under nitrogen to avoid adverse reactions due to oxygen and water. In the first step of the reaction, elemental sulfur, which is an 8-membered ring, must be reduced to S5-2 according to the following reaction. So here's our superhydride molecule, and this is lithium triethyl borohydride. We have a lithium +1 charge here. Then we have this borohydride molecule, which has a negative charge. And since the hydrogen atom is actually more electronegative than the boron atom, this hydrogen is able to leave with 2 electrons associated with it. So it can donate 1 electron to this system. And what we end up with, if we start with 2 of these, we end up with 2 triethylborane molecules. And we end up with this 5-membered sulfur chain in which the sulfurs at each end have a minus charge. Then we have 2 lithium ions, and then we evolve hydrogen gas. So in the second step of the reaction, S5-2 is reacted with titanosine dichloride to form bis-cyclopentadienyl titanium pentasulfide. So here we have our titanosine dichloride. We have our 2 cyclopentadienyl rings, and then we have 2 chlorine atoms attached to the titanium. We have our 2 lithium ions to counterbalance charges, and we have our 5-membered chain with each sulfur at the end having a minus charge. And so what happens is these sulfurs with the minus charge replace the 2 chlorine atoms here, and we end up with our ring, our final product, and we have a lithium chloride salt as a result. So let's move on to the actual process of this 2-step synthesis. Here we've got an overall picture of the apparatus needed for the synthesis. We've got a nitrogen tank here to supply nitrogen. We've got one line going to the gas manifold up here, and we've got another line going to a purge needle here that we're going to be able to purge the headspace of our bottle of superhydride. And we have our actual reaction flasks and condenser columns. We have a water cooling system that we can apply to those condenser columns. And then we have our gas bubbler here. And let's look at each one of these individually. First, we have a 2-stage regulator that's going to be used to supply our nitrogen gas. The gauge on the right is telling us what the total pressure inside the tank is. And this 2-stage regulator has a second gauge which tells us how much pressure we're actually letting exit the system, and that can be controlled with this valve. And we have 2 lines going out. This one is going to our gas manifold, and this one is going to our purge needle. So the purge needle is going to be used to purge our bottle of superhydride with nitrogen gas to make sure we don't have any oxygen in that headspace. And it's also necessary to create just a little bit of overpressure when we're getting our superhydride out of the bottle. Then we have the gas manifold. You can see this line coming in is supplying our nitrogen gas, and if we were doing this in person, we'd be doing 3 separate reactions, so we would have this valve, and this valve open. But since we're just going to be looking at one reaction, this is going to be the only valve that's open. And then there's an exit place for the nitrogen gas, and that's going to go to our nitrogen bubbler. Here we have our actual reaction flasks, and we have them over a stir plate, so we can put a little stir bar down here. And they're 3-neck flasks, and these are mainly so we can open these up and add our reagents and then put the stopper back on. And then we have the mineral oil bubbler, and this is to make sure that we don't create an overpressure in our system. So the nitrogen gas that we're supplying always has an open route to this gas bubbler, and so the gas goes down here and the tube extends down into the mineral oil, and so the nitrogen gas can bubble through here, and it just exits right here, and it creates a slightly positive pressure in our system without and safeguarding that we don't add too much pressure to our system. So let's look at how we're going to turn on the cooling water. We're not heating this reaction, but it might generate a little bit of heat, so we want to make sure we don't lose any solvent. So we've connected the water line here to where it connects to the bottom of the first condenser, and then it exits at the top one. Then it goes to the bottom of the second condenser, up to the top of this condenser, and then to the bottom of the third one, up to the top, and then exits in the drain over here. You can see as the water is coming on, it's supplying water to all 3 condenser columns, and it's exiting in the little sink over here. Supplying nitrogen gas to the gas manifold. As stated before, we have a 2-stage regulator here, and this gauge is going to tell us how much pressure is in the actual tank, and this gauge is going to show us our exit pressure, and we can control that with this valve here. If we turn this counterclockwise, we can get to where there's no pressure exiting the system. So the first thing that we'll do is we'll open up this valve to the gas manifold. And we'll make sure that this valve is in the position where there's no exit pressure. We're going to turn the nitrogen tank on, and we're going to slowly close down this valve until we see just a little bit of nitrogen getting to the gas bubbler. So as I was turning that valve, I was watching the gas bubbler, and you can see that we're getting about the right flow of nitrogen going through the system. Now we can purge the reaction flask with nitrogen gas. If I take the glass stopper off of the reaction flask and look at the gas bubbler, I can see that the gas flow is now going through the reaction flask and not to the bubbler. So I'm going to leave that there for a while, and when I put the glass stopper back on, I can see that the flow of nitrogen is diverted back to the gas bubbler. So at this point, we're ready to perform step 1 of the reaction. First thing that we're going to do is we're going to add our stir bar and our sulfur to the reaction flask. And replace the stopper. And so now it's time to get our superhydride solution. The valve to the purge needle was opened up, and what's going to happen is we're going to poke that needle just through the top of the septum to put a little bit of positive pressure of nitrogen gas in the headspace of that bottle. And then we're going to take our needle and we're going to draw up air or gas into the syringe. And so we're basically making sure that there's no oxygen in the headspace of that bottle at this point. So after doing that 3 times, now we're going to actually push the needle down to below the level of the liquid, and we're going to draw up 4 milliliters, and we're going to put that into our reaction flask. And you'll see that we're going to get an instant reaction and a lot of hydrogen gas being liberated. Okay, so at this point we're going to add a few milliliters of THF just to make sure that everything gets down into the reaction flask. I'm going to replace the stopper, and we'll set the stir bar. And then we're just going to let that react for 20 minutes. Performing step 2 of the reaction. At this point, we're just going to add our titanosyne dichloride, and then we're going to use another few milliliters of THF to make sure that we get everything down to the bottom of the reaction flask. So at this point, we can just let the reaction go for about an hour and a half. At the end of that period, now we're going to transfer our product into a 100 milliliter round bottom flask. So at this point, we are ready to go to the rotovap and distill off this THF solvent. Removing THF by rotary evaporation. Rotary evaporation uses a combination of temperature and reduced pressure to quickly evaporate and remove solvents from a system based on their boiling points. So let's go over the individual components of this rotovap. First, we have a water bath, and we can control the temperature of our solvent in this water bath. And then we have an armature that spins here, and by spinning, it creates more surface area inside that round bottom flask, which increases the rate of evaporation. And over here we have two cold fingers. This one right here is supplied with a circulation bath, supplies a cold fluid in here. And then there's a secondary trap right here filled with dry ice and isopropyl alcohol. And this is secondary trap is to make sure that no solvent gets sucked into our pump right here. And then finally we do have our vacuum pump here, and this is where we can control the internal pressure of the system. This is basically a closed system. You can open the system to the atmosphere here, but if that were closed and we had a round bottom flask on here, the whole system is closed. You can see that the vapor would go through the armature here. It hits this cold finger, and when it hits the cold finger, the solvent condenses back to a liquid and it falls into this flask here. And this black tube here connects this cold finger to this one, and then finally this tube goes down to our vacuum pump. Now the vacuum pump has a valve on it here that's open to the atmosphere, so if I close this valve all the way, I'm creating a near vacuum in this whole system, maybe down to about 1 torr. And if I open this valve up slowly, I can slowly increase the pressure within this closed system. And if I had this all the way open, I would be close to atmospheric pressure outside the system. So when we're doing rotary evaporation, we kind of want to find a temperature in our water bath that allows us to hit the boiling point of that solvent somewhere in between atmospheric pressure and real low pressures such as 1 torr. So here's a vapor pressure chart of tetrahydrofuran, and you can see right here, if I come over to about 40 degrees Celsius, I can see that the vapor pressure of the THF is about 40 kilopascals, which is approximately 300 torr. So the 300 torr is a really good spot to be in between atmospheric pressure and a near vacuum. So we're going to set the temperature to 40 degrees, and we're going to go ahead and rotovap off the THF. First, we're going to make sure that the vacuum pump is kind of open to the atmosphere. We don't want to turn the vacuum pump on and have so much pressure that we force liquid into this bump trap up here. So we're going to put our solution on there, put a Keck clip on there to make sure the round bottom flask doesn't fall off. And now we're going to start that round bottom flask rotating around so we can increase the surface area for the evaporation. And then we're going to lower that arm down into the heating bath. So at this point we can go over to the vacuum pump, and we can turn the vacuum pump on, and we can slowly start closing down that valve. And if we keep our eye here on the condensing column, we can see when we've reached the boiling point or when we're getting a good flow of THF that's condensing off of this cold finger into the flask down here. So right here you can see that we're starting to get some condensation. So we're right about at the sweet spot to where we've reached the boiling point of the THF at this temperature, and we can slowly start getting the vapors to come up through here, condense on the cold finger, and drip down into this flask here. We don't want to do this too fast, or we'll create a situation where we'll actually get the fluid to come up here into this bump trap. We want it to just be enough to where we're getting a good flow, kind of a slower flow of THF. And you can see now that we're getting some drips, and we're getting the THF to collect in the flask down here. So we're going to fast forward this a little bit until we get to the point where we're pretty much done with the evaporation. So at this point, we can open that system up a little bit to the atmosphere. And we can turn the vacuum pump off, and we can retrieve our product. Now we're ready to dissolve the product in dichloromethane and filter it through a bed of sea light. The reason we're going to do this is we want to get rid of as many impurities as possible, and our product will be really soluble in dichloromethane, but some of the impurities may not be as soluble, and they can get trapped in the bed of sea light when we filter it. So we're just going to put about a ½ inch of sea light in our filter, turn on the vacuum. We're going to get about 50 milliliters of dichloromethane. We're going to redissolve our product. And then we're just going to filter it through that bed of sea light. So at this point, we can transfer our filtered product back into our round bottom flask. And now we're ready to rotovap off our dichloromethane. So at this point, we just need to evaporate the dichloromethane from our product. In this case, the vapor pressure of dichloromethane at 25 degrees is about 400 torr, so the water bath in this case has been set to 25 degrees. We're getting our evaporation and our condensation. And when we cease to get any more condensation from our cold finger, we're done and we can retrieve our product. So at this point, it's just a matter of scraping that product out of the round bottom flask and into a weighing boat perhaps. And then we're going to carefully put that into a vial. And we have our final product. Tune in to video 2, where we'll see how NMR spectra collected at different temperatures can be used to determine the energy of activation and the thermodynamic properties of delta H, delta G, and delta S for the transition state of the chair-to-chair flip of cyclopentadienyl titanosine pentasulfide.